Okay, so now in order to form the distribution that we wanted, in order to figure out what's the distribution of slopes given our data, well, we need to multiply. Okay, and I'm going to say proportional to, which allows me to avoid having to write every single detail in here that doesn't affect the center and shape of the distribution. So I will say here that this is going to be E. I'll just write it again as X negative 1 over 2 sigma squared. Sum goes from I equals 1 to 3 of yi minus mxi quantity squared. Okay, multiplied by, okay, now we're multiplying by f of m, which is normal 0, 1. Okay, normal 0, 1, I just want to remind us, would look like this. It would be, according to the normal PDF, it would be f of m equals 1 over the square root of 2 pi 1 squared. We have a variance of 1. Or, I'm sorry, it's just 1 because that's already our variance. Times e to the negative x minus mu, or m minus mu squared, over 2 sigma squared, which is just 2 times 1. And so you can see that that greatly reduces to just negative m squared over 2. Now again, notice that this here is a constant. And so since I'm saying proportional to, I don't have to worry about that constant. I can express it just as the exponent, which contains our parameter in it, which is negative m squared over negative m squared over 2. Okay, now again, I have common bases. It's e to this times e to this. So that means I can add the exponents. Okay, so I will have that this is equal to, the previous result is equal to exp negative 1 over 2 sigma squared, sum from 1 to 3 of y minus mx squared, and that is minus m squared over 2. Okay, excellent. So what we have to do is we have to make this look like a normal PDF so that we already know it is going to be a normal PDF because it follows the shape of the normal PDF, and both our likelihood and our prior follow a normal PDF. So we just need to be able to write it into this form. 1 over, well, we don't even care so much about the square root of 2 pi sigma squared, but we do care about this portion where it needs to be in this form of negative x minus mu squared over 2 sigma squared. Okay, so I really, what I want to focus on here is this exponent, which is this piece right here. And I want to make these look similar to one another. And if I can do that, where notice that our variable of interest is m, so I have to be able to write negative parenthesis m minus mu squared, then I can actually figure out what my mean and variance are. Okay, so what we'll do is, I'm just going to expand this out. Okay, so we're just going to focus on the green box. If I FOIL this, I'll have yi squared minus 2 yi, or I'll say xi yi. I don't know why, but that's the way I prefer to write it. Negative 2 xi yi, and then plus m squared xi squared. Okay, that's just the FOIL of that. And now I will have the negative 1 over 2 sigma squared distributed across that, minus m squared over 2. We forgot the summation. Let's put the summation back in there. It's going to be negative 1 over 2 sigma squared, sum from I equals 1 to 3. Now the sum distributes just fine over these three terms. And so let's go ahead and do that. So we'll have, well, I'm going to leave that. I'm going to leave that -1 over 2 sigma squared factored out for now. And then I'll have the sum of the yi squareds. I'm just going to skip out on the I equals 1 to 3 for time being, since we have a lot going on here. And this, notice, only sums across the indices, so I can factor out the 2m, because that doesn't depend on the index. Sum of xi, yi, plus m squared, sum of xi squared, and minus m squared over 2. So you can see already how involved this gets, and everything's perfectly normally distributed. There are just lots of details that need to be worked out. So now what we're interested in is the parameter m squared, recall. And so if I rearrange this and distribute, I'm going to write this as the sum of xi squared, negative sum, over 2 sigma squared. That's just me distributing into this last term over here, multiplied by m squared. Okay, there's my m squared. And then I will write the distribution across to the second term, which will just give me plus 1, nope. That will be not 1, but the sum of xi, yi over, now the -2's will cancel, and so we'll be left with times m here, and just over sigma squared. Finally, this last term here will be the, distribute that here, we'll get minus the sum of the yi squared over 2 sigma squared minus m squared over 2. Okay, now notice that this first and last term, these are both quadratic in m. Remember, we're focusing on m here. That's our variable, our random variable. And so I can rewrite that term as, if I factor out an m squared from them, then what that will leave me with is negative sum of xi squared over 2 sigma squared minus 1/2. Okay, that's just my coefficient, doesn't depend on m. It's all only dependent upon the givens. And then this guy stays the same. And this guy is also, oh, this is times m, and this is our constant. And the reason I write it like this is because we should recognize this as being of a special form. You can kind of think about this as a times x squared plus what we would typically call b times x, and then this whole piece we write plus c. Then we have a quadratic function in the variable m. Since this is all based upon proportionality, one of the additional features that we can use here is anytime we can factor out a constant, it makes sense to do that, because we're saying that this is not equal to, this is all proportional to the variable piece of the normal PDF, right? We were able to ignore this entire statement here because it didn't depend upon all. Now, that's exactly what we're going to do with this third term here. This is c. And recall that this is all e to this power right here. And when I have an exponential that has the sum or difference of terms, I can actually write this as e to the first term involving m squared times e to the second term involving m times e to the c power, right? So it's kind of like saying, if I have e to the ax squared times e to the bx times e to the c, that by common bases is equal to the sum of those exponents. But the other thing I can do is I can go in either order. I can take 3 factors and make them 1, or take 1 factor and make them 3, or even 2. So what I'm going to do is this e to the c, I'm going to write this as e to the ax squared plus bx times e to the c. And that's going to be e to this piece right here. And notice that this doesn't depend on m. Does not depend on m. So once again, I'm going to use that proportionality idea and say, well, this is actually proportional to e to the ax squared plus bx. And what that allows me to do is just focus on these 2 terms here, which I will go ahead and write. E to the, so that leaves us with just taking off from here. That is going to be, for this term, negative sum of xi squareds over 2 sigma squared minus 1/2 times m squared plus the sum of xi yi over sigma squared times m. Okay, now what I want to do here is, in order to get it into this form, I am going to need to somehow complete the square, right? Because what I want to do is I want to be able to express it as m minus something squared, but when we have ax squared plus bx, we would need to both add something and subtract something to make this a perfect square. Okay, so I need to make this a perfect square. And that might be hard to see right now, just because of the fact that there's a lot of stuff going on here. Well, let me refer to the coefficient of m. I'm going to refer to this right here as a, and I'm going to refer to this whole thing right here as b. Okay, so we have am squared plus bm. Now, if from that I factor out an a, then that will leave me with m squared plus the b over a, because I just pulled out an a, times m. And the reason that this is convenient is because to complete the square on this, you would take the coefficient here, which is b over a, it's that coefficient, divide it by 2 and square it. And that would be the term that we would want to add and subtract. You'll see in a moment how this works. So what I will do is I will add, which will be b squared over 4a squared once I square that, and then I'm going to want to subtract b squared over 4a squared. Okay, now these 2 terms, what will happen is, oh, and I will actually want to add this into the parentheses, like so. That's still a true statement. These 2 will still add up to 0, but what this will give me is a times m plus b over just this, what's here in the parentheses, which will be b over 2a. And notice that if you square that, if you FOIL this out, you'll get m squared plus 2 times, oh, sorry, there should be, not an m here, excuse me. If you FOIL this out, you'll get m squared plus 2b over 2am, which will just be b over am, that will give us that term, plus this quantity squared, which will be b squared over 4a squared. But then we have this residual term here, which we'll just write minus b squared over 4a squared. Okay, so what that has just expressed to us is that that is the exponent of everything related to m. Okay? Now we recall that this is just all the exponent right here, is this component here. And again, notice that this does not depend on m. And remember, anything that does not depend on m, that can be broken up like we did here, where we can apply this property again. This is all just the exponent, so we can take this e to the negative b squared over 4a squared, and we can factor that out as e to the negative b squared over 4a squared. So what we really just need to focus on is this piece right here. And the reason that we just need to focus on this piece is that it's already taking the shape of the exponent of a normal PDF, which has in the exponent negative quantity x minus mu squared over 2 sigma squared. Now, all I need to do here in order to get it into this form, notice that it's already taking on that shape. So what I can do is I can actually write this as a, okay, which I am missing a 2 sigma squared in the denominator. So what I can go ahead and do here is I can say that this is 1 over a to the negative 1, right? Because that is the same thing as just a. So if you take 1 over a to the negative 1, that will just give you the reciprocal, which is a to the positive 1. And now you can see that it's starting to look a lot like this, but in the parentheses, I have my variable. It has to be minus. Okay, well, it's a plus sign here, so to keep it a plus sign, I would have to do minus b over 2a. And it's that quantity squared. Now here I'm kind of missing a 2, right? So one thing that I can do is I can go ahead and multiply and divide by a2. So here's how I'll write this. I'll write this as 2 times that. I want it to be a negative. I want it to be a negative. So the way I would get it to be a negative, and it's all just playing around with symbols here, I can make this negative 2 times 1/2 of A inverse. All right, so notice that what we are describing is pretty much in the correct form. M minus negative b over 2a squared all over negative 2 times 1/2 a to the negative 1. So now that it has this shape, this right here is going to be our mu, and this right here is going to be our sigma squared by inspection and by matching things together. Okay, so let's unpack what mu is in terms of this b over a. Mu is going to be negative b, so negative sum of xi yi over sigma squared. Okay, that's the negative of b over 2a. A is negative the sum of xi squared over 2 sigma squared minus 1/2. And that is our A value right there. Okay, we can do some work on this. And really that amounts to just canceling out the 2's. We could stop here. We already have our mean. But, if we cancel that out, it just makes the expression a little bit neater. So that's the mean. That's how the mean is calculated. Of course, the mean depends upon the standard deviation. And what's the standard deviation? Well, the standard deviation, remember, this sigma squared came from, that's specific for the variance, not of m, because remember, now we're finding the variance and mean of the distribution of m given the data, and this sigma squared comes from the variance associated with the error in our model. So we should also write for our variance here that we should call this sigma m squared to distinguish it from the variance that came from our expression for the error term. Okay, so sigma m squared is just going to be 1/2 of A inverse, which will be 1 over this quantity here. So 1/2 times, let's see here, 1 over, it'll be 1 over this quantity here. Oh, I'm sorry, this should be a negative 1/2 because we factored out a negative sign here, so these negatives have to cancel. So this will be, let's see, negative 1/2 times 1 over the sum of the xi squareds over 2 sigma squared minus 1/2. Okay, now if you factor out a minus 1/2 here, that will cancel out with this minus 1/2. So this is just simply, I'm gonna leave it as an, well, actually we could say 1 over the sum of the xi squared over sigma squared. Remember, this sigma squared is associated with the normal 0, 1 distribution of the error term. And then if we factor out a negative 1/2 there, we'll have plus 1. Awesome. All right. So now we know that m, given the data, I'll just write that, m given the data, given our data that we've observed, is a normal function with mean, normal function in M with mean mu sub m standard or variance sigma m squared, which are these two quantities that we now have come up with. So you can see this is a tremendous amount of work, and these were pretty well behaved functions. So with this notion of conjugacy, it is extremely helpful in knowing what kind of distribution you end up with, what kind of mean and variance it will have. If the prior were not conjugate to the likelihood, meaning that the posterior followed a different distribution, things could get out of hand pretty quickly. Now let's take a look at what we would actually have here in the situation where we had the data that we had. We would end up with a mu sub m of 2.01. We would have a variance of 0.01 when we plugged our data into the expressions that we just came up with for mu sub m and for sigma sub m squared. So plugging those in here, we would end up with a mean and variance of 2.01 and 0.01. Now remember, in our prior, this is our prior, this dotted curve, this is our prior assumption about the distribution of m. Remember, we assumed that it was normal 0, 1. But after analyzing it with respect to our data, our posterior, after data, so this is before data was collected. Now that we have our data, we can say that m has a mean of 2.0 and a variance of 0.01. So remember what we said earlier, that the slope should be around 2? It made sense, it was pretty close, but it had some errors. Well, this is reinforcing that. It's saying that our mean should in fact be 2, but that, depending on the data set that you get, there could be a bit of variability in what the true value of the slope should be. So recall back up here, we said, hey, you know what? If m was equal to 2, then you'd have these small errors. And again, because every random sample is going to be just that, random, then every n that we come up with on each data set might be slightly different. But given the data, it should be mean 2.01 with the small variance of 0.01. So the prior distribution was fairly uninformative, had large spread, uncertainty. However, given the information, the data, we can observe that the posterior distribution provides far more certainty about the correct slope being near 2.01 with a small variance of 0.01. Not only that, but it is a normal distribution. Okay, so the complexities of posteriors and conjugacy, this is with conjugacy. If we did not have conjugacy, things could get even more complicated more quickly. But this is just sort of a deep dive into some of the mathematics that we would have to go through with conjugacy.